All right, good morning, everyone. So let's begin our lecture today. I think the university updated some of the safety features, so the Zoom becomes more complicated, and hopefully I can figure out the waiting room thing. I didn't hope. The first thing is last lecture we talked about CEP, which means the critical extreme position design. So that's one of the example we discussed. So in the end of the lecture, we introduce the polynomial method. Basically, we assume your S theta, it can be described by a polynomial, and then the order of that polynomial depends on the boundary conditions. And if you look at it here, look at section number 2, we have two boundary conditions on displacement, and then we also have two boundary conditions on the velocity, two boundary conditions on the acceleration. So for CEP, that's actually very special. That means you already know once you pick your segment, you already know all the boundary conditions. So typically, you usually choose a polynomial up to fifth order. That should be always true for CEP. But then in this class, we're going to talk about CPM, critical path motion design. So in this case, in some of the segments, you're not going to see all the boundary conditions, and then that makes things more complicated. So let's refresh our mind. So last time I mentioned we are talking about 3 different domains. We have t, you have theta, you have your x, right? So between time and theta domain, your theta is the angle of your cam. I think it stands for critical path motion design. So this is just a concept. So between theta and t, we usually know that the angular speed of your input cam is theta dot, and then we know the time is t, and then velocity multiplied by time, that's going to give you the actual position. And then between x and theta, the x is actually intermediate step. We're trying to scale your theta such that theta over beta, such that no matter what your theta range is, your x is always in the range of 0 and 1. So theta naught. So let me see. Your theta is in the range between theta naught and theta 1. So theta naught is a starting point of your theta, and then beta is the width of that range. So basically theta 1 minus theta naught. All right. So there are a few things you need to remember. So we're talking about, so as I said before, so in order to do cam design, so eventually what we need to find is S theta. So that's our target. That's finally what we need to find out. And then in order to find that S theta, there is one critical requirement, which means your V theta and A theta are continuous. So that's our design requirement. We want to find the S theta under the conditions that your V theta and the A theta are continuous. Okay, that's a strict one. And then in practice, you might see other design requirements saying, okay, we want to minimize the amplitude of A theta, but then that's for optimization. Then you need FMecon or other MATLAB or other software for you to design, for you to optimize. But right now, we just focus on one single design requirement. So that being said, so most of our design, our design parameters is going to given in time domain. So what we do is we usually write displacement in time domain as st, velocity in time domain as vt, acceleration in time domain is at. So if you look at the units, your s is a displacement, so the unit is meters, and then your velocity is meters per second, acceleration is meters per square second, right? Eventually you want to design your theta, so let's write these as theta, s theta, v theta, and a theta. Okay, so your s theta is a function of theta, so let me write it a different way. So the unit here is meters again, but then your velocity is meters per radian. That's because your v theta by definition is ds theta, d theta. So remember the definition for your SVAJ diagram. So the velocity diagram is not a time, it's not a time derivative, it's a theta derivative. So that's something you need to always keep in mind. Very special. So it's the same thing, acceleration is meters per radian square. Okay. So then what about x? So we also name the displacement in the x domain as sx, and then you have velocity in x domain, you have acceleration in x domain. So as you can see, your x is actually unitless, right? So on top you have a unit of radian. The beta has also a unit of radian. So that's why your sx is actually unitless, v is unitless, and a is also unitless. So usually in order to make sure we can transfer data between these three domains, we usually change the unit of sx so that they have a unit of meter. The reason we change that is if you look at your sx equals to a summation from 0 to n ci x I. So that's the polynomial we use to describe the polynomial in an x domain. So your x is unitless, but then what we can do is you can give a c, the coefficient has a unit of meter. So that your xx also have the same unit meter. So by doing so, if you check the units, then you can find a very special row, which is the first row. You can see that in three different domains, you have st, you have s theta, you have sx. You have all these different displacement representations in three domains, but then they all have the same unit. So that's the reason why we can directly transfer displacement data between different domains. Okay, so basically that's the internet between three different people. So you have t, you have theta, you have x. In order to communicate with each other, you have to use displacement. There's no way you can directly dump velocity because they're in different domain, they're in different unit. So they're actually different things. So how can we couple these velocities? So last time I mentioned that we can use chain rules, but here I'm gonna directly provide you the relationship. So between v and vt and v theta, so what you're using is, let me see. Let me insert one page. Okay, so let me write it in a different way. So you have your theta domain, you have your t domain, you have your X domain. All right, so between T and X, your AT is theta dot over beta square AX. Your VT is theta dot over beta Vx. So I'm skipping the derivation here. Okay. So I think in my video and also in my lecture notes, I derived these relationship using chain rule. So if you're interested, you can go back and check it out. But here, I directly give you the result. And then between X and theta domain, you have Vx over beta equals to V theta, Ax over beta square equal to A theta. And then between theta and time domain, then you can do the derivation. So you have V theta times theta dot equals to Vt, and then you have theta dot squared times A theta equals to At. So that's the relationship we need to get. So the note is, if you want to transfer boundary conditions between different segments, you can only do it in either theta domain or in time domain. You cannot transfer boundary condition information in X domain. So that means your X domain, oh, sorry. So your X domain is a local coordinate in a specific segment. So your X domain basically is a local coordinate for one segment. If you want to transfer information between segments, then you cannot use this local coordinate. You have to use either theta or time domain. That's the only domain you can transfer data between segments. All right. We're gonna use one example to see how that's gonna working. Let me see if anyone is in the waiting room. Nope, that's cool. All right, so let's keep this in mind and then move on to example one. I created a video for that. I also scanned the textbook for this example and posted on Blackboard, so you can check it out either way. So here we have a CPM problem. So it has 4 different steps. First acceleration, then maintain the speed, and then deaccelerate, and then return to the original position. So naturally, this gives us 4 segments, right? That's your segment 1. That's your segment 2. And then your segment 3 and segment 4. So as I said, the very first step is always trying to plot your SVAJ based on the information you already know. So you have your S theta, and then you have your V theta. So here I use a subscript to describe which domain we are talking about. And then eventually you have your A theta. All right. So we know that it has 4 segments. One, 2, 3, and 4. We have no idea about what's the width of each segment, but we can just first divide the entire segment into 4 pieces. So it's from 0 to 2 pi. That's something we know. Okay, so we have the coordinates. Then the next step is, let's see what information we have. So the most the information that we have the most understanding is the second segment. So we start from there. So in that segment, we have a constant speed in 10 meters per second for 0.5 seconds. So everything is given in time domain, as I mentioned before. That's the design requirement. But then in order to plot everything in theta, we have to convert time to theta. We know that the cycle time is 1 second. That means your period is 1 second. So the speed, theta dot, is 1 cycle versus 1 second. So that's 2 pi radian per second. All right. So that means in 0.1 second, your cam is rotating by 180 degree or pi radian. So that means your second section or segment should have a width of pi. Okay. And we also know that the velocity is a constant 10 meters per second. But we also, so if you go back to here, we know your VT is 10 meters per second. And then we want everything in V theta, right? So that's why you have to pick these equation. And then we know that your V theta is VT over theta dot. So your VT is 10. Your theta dot is 2 pi. So eventually your V theta is 5 over pi. So that means, okay, in this case, we know the second segment has a constant speed, and then this speed in V theta domain is 5 over pi. Because the speed is constant, so that means your acceleration is 0 in this domain. All right, so just from the statement number 2, we're able to get this much information from for our SVAJ plot. And then what else? So we know that the acceleration, then we look at the acceleration. First of all, it accelerates from 0 to 10 meters per second. So that means it starts from 0 velocity, and then it accelerates to this point. But it doesn't describe what it looks like between these 2 points. So the profile is still questionable, okay? And then let's look at the deceleration, step number 3. So the follower goes back to 0 velocity. So that means it goes back to 0 velocity. And then eventually it returns to the starting point, okay? So we know that it starts at 0 and it ends at 0. All right, so that's all the information we have. So make sense? Okay, so in order to start our design, we have to find the boundaries of all these segments. So in this case, we assume that this first segment has a width of pi over 6. And then if that's the case, then this is 7 pi over 6. And then we also have assumed that segment 3 is also 30 degree. So that's 4 over 3 pi. And eventually that's 2 pi. We have 120 degree for the last segment. So all the purple numbers, they're provided by randomly. Yes, exactly. So we choose 30 degree just by an example. So in practice, as I said before, if we go back to the very beginning, I mentioned that we only care about one design requirement, which means your V and A should be continuous. But in practice, we also want to reduce the acceleration of your A. So that means once you have this design, you might want to fine tune these purple values such that your A theta has the minimal amplitude. But then you're just doing the camp design thousands of times and pick the one that you want. So you can use MATLAB to help you to do these automatically. But here we just use one example, which are the purple values. Okay. So once we give this information to the design, then we can focus on each segment, right? So first, segment number 1. So let's draw it out, what we have. So we have segment number 1 as theta. We have V theta. We have A theta. So we know that it starts from 0. It ends at 1/6 pi. And then we can name these as theta naught. That's the starting point of that segment. And then theta 1, that's the ending point of the segment. And then beta is theta 1 minus theta naught. Again, it's 30 degrees. Okay, so we use a different color to label all the boundary conditions we know. So as displacement, we know the starting point, but we don't know the ending point. At the velocity, we know the starting point. We also know the ending point. At acceleration, we know it has to end at 0, but we don't know the starting point. So here, it should be somewhere in here. We put a question mark. Oh, it may not be 0. So, oops. So here's what is the acceleration at theta equal to 0? We don't know, so we put a question mark. Okay, so that's all the boundary conditions we know. And then we already know that in order to describe your Sx, we need to use a polynomial, I equal to 0 to n Cixi. And then the number n is determined by number of boundary conditions, BC minus 1. So BC stands for boundary conditions. So how many n, what is n value determines the number of boundary conditions minus 1. So we have 1, 2, 3, 4 known boundary conditions. So that means your n equals to 4 minus 1 equal to 3. Okay, so you can write it out. You have your Sx equal to C naught plus C1x, C2x, C3x third. And then you can find your Vx, C1 plus 2C2x plus 3C3x squared. You can find your Ax is C2 plus 6C3x. So in order to find that polynomial, we have 4 unknowns, then we need 4 equations. So naturally, these equations can be derived from your boundary conditions. Okay, so what boundary conditions we know? We know everything in theta domain, right? So we already know that value is 5 over pi. Okay, so let's write out all these boundary conditions. We have as theta, when theta equal to 0, that's 0. We have, let me see. We have V theta when theta equal to, let's put a theta naught, that's more universal. That's 0. We have V theta when theta equal to theta 1, that's 5 over pi. We have acceleration in theta domain when theta equal to theta 1, that's 0. Okay, so we have all the boundary conditions in theta domain, but then as I said, all the equations are in x domain. So that means we need to convert everything from theta to x. So let's find out all the boundary condition equations. Your x domain, when theta equal to theta naught, that means your x equal to 0. always remember that when x equal to 0, that means where your theta starts. When x equal to 1, that's when your theta ends. So Sx, that's where your theta starts. So your Vx, x equal to 0. The third one is where your theta ends. So your x becomes 1. Ax, x becomes 1. And then 0, again, as I said, all the displacement information can be directly copy and paste. So 0 becomes 0. In order to find the velocity relationship between theta and x domain, then you have to go back to this triangle between theta and x. Okay, so v theta is Vx over beta, and then A theta is A theta over Ax, sorry, over beta square. All right, so then you can use these two linear equations to convert your boundary conditions. The trick part is when you have velocity and acceleration at 0, then you can also copy and paste. But then in this case, your v theta is not 0. So that means your Vx is going to be beta times 5 over pi. And then remember, your beta is pi over 6. So that means it's 5/6. So make sense? So the tricky part is here. When you want to find the equations for in X domain, you have to carefully transfer data between domains. Then you always need to go back to the triangle I provide you. So 1, 2, 3, 4 equations. 1, 2, 3, 4 unknowns. So you can go back to my notes and find out the polynomial. Let me see if I have the solution here. Okay, the solution here is C0 is 0, C1 is 0, C2 is 5/6, C3 is minus 5 over 18. That's a good one. CPM. No, that triangle works for both CPM and CEP. I think that triangle also works for, there's one thing I'm not sure. If your cam velocity is not constant, then that triangle might change. But then here we only talk about constant cam input. Then we can use a chain rule, so that makes life easier. All right, so once you have all this information, then you can find out your Sx, right? Its polynomial is from 0 to n. Let me write it down. Your n we already know is 3. It's dixi. So once you know your Sx, you can easily find your S theta, right? So that is from 0 to 3 ci. You just replace your x by theta minus theta naught over beta. So that's by definition. Remember, this one is the one we need to find out. That's our design. So you cannot end it up in X domain. You have to transfer everything to theta domain. In the exam, you need to present this as your final solution. So why this is important? Because once we know the S theta, you can derive for V theta. You can find your A theta. And as you remember, so there are two question marks in these plots. So this question mark is not important in this segment, but it's very important to the next segment, right? for example, here, your segment number 2 should start at this point. So that's why we have to calculate these out before moving to the next segment. Okay, so what is the theta as theta here for this question mark? So what you do is, for segment number 1, your sine theta 1 equals to pi over 6. So that's, this point is your S theta when theta equals to pi over 6. And then this point is your A theta, theta equal to 0. And then remember, these S theta and A theta, they are the solutions for segment 1. Basically, they are the solutions you just got. And then I'm going to give you the direct information directly. That's 5 over 9. And the acceleration, let me see. Second one. So we know that the AT at time equals 0, that's 240 meters per square second. And then your A theta at theta equal to 0, that should be AT divided by theta dot square. It's not clear. That's how you find your A theta. Okay, so that means once you finish one segment, you should be able to find all 6 boundary conditions for that segment. So here, after that derivation, we already know these boundary conditions. We already know these boundary conditions. Then we can move on to other segments. So let's see. We have segment number 2. So again, nothing special, just copy and paste. We know it's starting from theta, and then it's from theta naught to theta 1. And then that's your S theta. And then that's your V theta, theta naught to theta 1, V theta. And then you have your A theta, theta 1, theta naught, A theta. Then we need to find out what we already know. So we know that, okay, your velocity is constant, 5 over pi. So that means your velocity is constant, 5 over pi. Your acceleration is constant at 0. And then your displacement, because your velocity is constant, so that means your displacement should be a linear line. And then the slope here is 5 over pi, right? And then that means your S theta, in this case, it can be written as 5 over pi times times theta plus a k value. That's how you describe a linear function, right? If you know the slope. What you need to know is just the crossing point, right? The k is a crossing point on the y-axis. So how can you find the k? Because as I mentioned before, from segment number 1, we already know these values, 5 over 9. So that means when theta equal to theta naught, your S theta should be 5 over 9. So that means when you know the entire velocity for one segment, you don't need to solve a lot of equations. Just one equation will be okay. And then your theta naught is pi over 6. And then you have the equation is 5 over pi times pi over 6 plus k equal to 5/9. Then you can find your K values. So eventually, your S theta is 5 theta minus theta naught over beta plus 5/9. So in this case, your theta naught is pi over 6. Your beta is theta 1 minus theta naught is, again, that is different because the width here is pi. Again, once you find your S theta equation, the next step is to finish that segment. You need to find all the boundary conditions, all the 6 boundary conditions we're talking about. So here we already know 1, 2, 3, 4, 5 boundary conditions. Then you need to find these points, what that data is. So that's S theta when theta equal to theta 1. And then you can plug this back in. And then let me give you the information. That's 50/9. So once you find all the boundary conditions, then you can move on to the next step. All right, so any questions? So the tip for solving CEP is, sorry, yes, the tip for CPM is you have to solve the problem segment by segment. And then you always start from, you pick one segment to start. And then once you find the S theta for that segment, then you have to complete all 6 boundary conditions for that segment and then move on to the next one. So let's look at segment number 3. The same thing. You start from what you already know. So you know it starts from theta naught, ends from theta 1. So what is theta naught again? I forgot. What's the starting point of the segment? Okay, it starts at 7/6 pi and it ends at 4/3 pi. That's your theta, that's your S theta. And then you have your theta, V theta, theta naught, theta 1. And then you have acceleration, theta, A theta, theta naught, theta 1. All right, that's everything you already know. And then let's look at the very first plot we have. So we have 1, 2 boundary conditions from there. We know the starting acceleration. Oh, we actually have 3 boundary conditions there. We know the starting velocity is 5/pi, and it ends at 0. Acceleration starts at 0, but that's all we know. So that means, let's go back to these. We know that it starts from 5/pi, it ends at 0. Acceleration starting point is 0. So we remember, we already know the boundary conditions for the displacement. That's from the ending point of the previous segment. So this point is 50/9. Okay, so that's everything we know for segment number 3, right? So let's count how many boundary conditions we have. 1, 2, 3, and 4. If it's 4, then we can assume that your S theta is C0 plus C1x plus C2x squared plus C3x cubic. And then you can actually copy and paste to find all the other diagrams. All right. So that's the equation, that's the polynomial you need to find. You have 4 unknowns there. So we need to find the equations in X domain, right? Oh, sorry, I think I'm a typo there. That should be your SX. That's your VX. That's your AX. So because your polynomial is in X domain, but as I said, all the boundary conditions are in theta domain. So it doesn't really matter. You just copy those boundary conditions first. Theta equals theta naught equal to 50/9. V theta equal to theta naught. That's 5/pi. And V theta equal to theta 1. That's 0. A theta equal to theta naught. That's 0. So that's all the boundary conditions you have in theta domain. Again, you want to go from theta to x, so you can solve these equations. Your S, x equal to 0, because theta naught corresponds to x equal to 0. And its displacement, you can directly copy and paste. And then Vx, x is equal to 0. Vx, x equal to 1. And then Ax, x equal to 1. And then the next step is to find all the 0 velocity and accelerations. So if it's 0, then you can directly copy and paste. Okay, so here you have one unknown. You have one non-zero velocity. So how can we convert that? So your Vx over beta equals to V theta. So remember that your beta is theta 1 minus theta naught. So beta is different in every segment. So you have to calculate your beta in each and every segment. In this case, luckily we have the same beta. The beta, which the width is still pi/6, but that might not always be the case. So your beta is a property associated with your segment definition. So you have to find a beta for each segment individually. So in this case, your beta is the width is pi/6. And then what is your V theta, Vx then? Your Vx is just V theta times beta, right? Is 5, 6. You got the same boundary conditions, 5, 6, as the segment number 1. That's just an accident. That's because we choose the same segment for, we choose the same width for segment 3. But in practice, that might not always be true. You cannot directly copy and paste. You cannot say, hey, this is 5/pi, so your Vx should be 5/6, because we already calculated in segment 1. So that mindset is incorrect. All right, you have 1, 2, 3, 4 boundary equations, and then you have 4 unknowns. By solving them, you can find out your C naught equals to, let me see, 50/9. C1 is 0. C1 is 5/6. C2 is 0. C3 is -8, 18. Okay, so let me mention that thing again. So in here, in the very first segment, so we already convert a velocity. We also find the velocity in theta domain is 5/pi, right? And then we convert it to velocity Vx, and then that gives us 5/6. And then if you move to segment number 3, your velocity in theta domain is again 5/pi. Usually, most of the time, you cannot directly copy the information on the right in another segment. You cannot directly copy the 5/6. But in this example is very special because your beta is the same in both segment 1 and segment 3. So that's why you can directly copy and paste. But to avoid any potential mistakes, you have to calculate these from that relationship for each segment. You cannot directly copy and paste. So that means if I change the width of segment 3, these boundary conditions on your in the X domain may no longer be 5/6. Perhaps I just make things more complicated. So I should say that if you have your boundary conditions in X domain, always use this equation to find the boundary conditions in X domain. And then remember, these beta might be different for each segment. All right, so once you have all this information, then as I said, the last step when you design one segment is trying to complete all the boundary conditions. Here, you need to complete this boundary condition, and then you have to complete this boundary condition. So I can give you the information. Let me see. That's 3. So this is when your X equal to 1. I forgot. Did I have that somewhere? Anyway, so the only thing I remember here is this acceleration, A, when theta equal to theta 1. In time domain is minus 24, it's minus 240 meters per square second. And then you can convert it to a theta. So that gives you a theta of so I forgot this value, but you can calculate these out. If you have AT, then you can follow in the triangle to find your A theta. And then in here, you just substitute your S, X equal to 1 to find this ending point. Because in displacement, you can directly transfer the data no matter which domain it is in. All right. So the last segment, I'm not going to go over it again because it's just repeating stuff. So for segment number 4, the same thing. You draw your theta as theta. It starts from theta naught equals to for third pi. It ends as theta 1 equal to 2 pi theta v theta theta a theta. The same location, theta naught, theta 1, theta 1. Okay, so usually the last segment, yes, that's the right calculation for a theta, but I don't have the numbers ready. So that's your S theta. So let's find out what we already know. So we know that your S theta 1, we already know that's the value we calculate from this step. And then we already know it should end at 0. And then we already know the velocity is initially 0. And then the acceleration, this acceleration is calculated in segment 1. That's calculated in segment 3. All right, so this acceleration is also calculated in segment 3. And then the velocity, we know that is phi over is 0. Okay, so here you can directly get 3 boundary conditions from the problem description. And then the rest 3 boundary conditions can be calculated from other segments because, as mentioned before, one of the crucial design requirement is that your S, V, A, and J should be continuous. So that's why your boundary conditions should connect between different segments. So here you have 6 segments, then you have 6 equations. So you can assume that your Sx is I equal from 0 all the way to 5th order Cixi, because you have 6 boundary conditions. So that's why you have to use 5th order. And eventually I'm going to give you the solution here. All right. So that's the end of for CPM. So you can see that your CPM is more complicated than CEP. That's because of the boundary conditions. In CEP, because we only care about the displacement, and displacement can be directly transferred between domains. So you don't have to worry about how to transfer velocity and acceleration data between domains. But here, because we also have design requirement on velocity, so you have to transfer these data between domains. So that, then remember, you have to go back to that triangle. And then the most important thing is, in that triangle, your x domain is a local coordinate. So if x is a local coordinate, then your theta naught, theta 1, and beta, they are all local. When I say they're local, that means they might be different in different segments. If you move from segment 1 to segment 2, then you have to recalculate your theta naught, theta 1, and beta. So I think that's it for today. And I already posted homework number 6 online. And hopefully you can solve that by yourself. I'm going to go over it briefly on Tuesday and then post the solution by the end of Wednesday.